Hello everyone, we are given a 250 volt DC shunt motor with an armature resistance of 0.2 ohms and a field resistance of 100 ohms. When the motor is operated on no load, it draws an armature current of 5 amps and runs at 1200 rpm. When a load is coupled to the motor, it draws total line current of 50 amps at rated voltage with a 5% reduction in the air gap flux due to armature reaction. The voltage drop across the brushes is to be taken as 1 volt per brush under all operating conditions. We have to find the speed of the motor in RPM under the loaded condition. To know more on the concepts used to solve this problem, kindly refer the NPTEL Electrical Machines course, Module 8, Lecture 3 by Professor G. Bhuvaneshwari of IIT Delhi. We will be using the following concepts to solve this problem. The voltage equation of the DC shunt motor is E equals EB plus IARA plus VBD, where V is the applied voltage, EB is the back EMF developed, IA is the armature current drawn, RA the armature resistance, and VBD is the total voltage drop at the brushes. The back EMF developed is proportional to the speed and the flux per pole. EB is proportional to 5 times omega. We'll now start solving the problem. I'll first write down the given values. So the rated voltage V equals 250 volts. The armature resistance RA equals 0.2 ohms. The shunt field resistance RSH equals 100 ohms. And the percentage reduction in flux due to armature reaction under the loaded condition is 5%. Under the no load, the armature current drawn IA0 is 5 amps. The no load speed is given to be 1200 rpm. In the loaded condition, the total line current drawn is 50 amps. Also, we are given the brush drop per brush equals 1 volts. So we have to find the speed under the loaded condition. First, I just draw the circuit diagram of the shunt motor. So we'll have the armature resistance RA, the armature with the brushes, and the shunt field. So the voltage will be applied here. The line current drawn, and this is the armature current. This is the shunt field current. Back EMF will be developed here. Now we have to find the back EMFs under both the conditions. So we'll just write the KVL for the system. So V equals EB plus IARA plus VBD, and we'll substitute all the given quantities. So V is 250. We have to find EB. Let's take it as EB0 for the no load condition, plus IA for the no load condition is 5 amps and RA is 0.2, plus VBD is the total brush drop. So we have 2 brushes here and voltage drop per brush is 1 volt. So the total voltage drop will be 2 volts. So we'll solve for EB0 from this. EB0 equals 250 minus 5 times 0.2 is 1 minus 2. So that is equal to 247 volts. Now similarly, we'll find EB for the loaded conditions. But before that, we have to find the armature current since only the line current is given. So here you can see that you can apply KCL at this node to find Ia in the loaded condition. So Ia equals IL minus ISH, which is equal to IL minus ISH is nothing but V divided by RSH. So which is equal to IL given as 50 minus V is 250 divided by RSH is 100. So which is equal to 50 minus 2.5. So this will be equal to 47.5. Now let us find the back EMF. So the back EMF, we can use the same equation. The only change will be the armature current. V equals EB plus IARA plus VBD. So V is 250 equals EBL plus IA is 47.5 amps times RA is 0.2 and VBD remains the same, which is 2 volts. So now we can solve for EB loaded. So EB loaded equals 250 minus 47.5 times 0.2 minus 2, which turns out to be 238.5 volts. So we have both the back EMF. Now we can proceed to find the speed. So we can relate the back EMF, the speed and the flux as EB proportional to 5 times omega or 5 times N. So omega is in radians per second and N will be in RPM. So in the no load condition, EB naught equals some proportionality constant K times 5 times N. And in the loaded condition, similarly, there will be the same proportionality constant phi L times NL. So we can divide these two equations to get EB naught divided by EBL equals the proportionality constant will get divided. So phi naught divided by phi L times N naught divided by NL. Now we can take NL to the other side. So NL equals, and this to the other side, EBL divided by EB naught times phi naught by phi L times N naught. So we have N naught, EBL and EB naught, but we don't have this ratio. So this ratio of flux can be obtained from the given quantity that there is a 5% reduction in the flux due to armature reaction. So which means phi L, which is the flux under loaded conditions, has reduced by 5%. So it will be 95% the value under the no load condition, which means this will be equal to 0.95 times phi naught. So we can write phi naught by phi L equals 1 by 0.95. Now we have all the quantities on the right hand side, so we can find the loaded speed. So I'll substitute everything. The loaded speed equals EBL, which is 238.5 divided by EB naught is 247 times this ratio is 1 by 0.95 and the no load speed is 1200. So now when you solve this, you will get this as 1219.68 RPM. This is the speed under the loaded conditions. So now we'll look for an option which is close to this value. So the option which is closest to this value is option C, which is 1220 RPM. So the correct option is option C. Thank you.